It really feels like magic sometimes.
Oh, absolutely.
Like when you watch an AI system perfectly transcribe a super messy audio recording.
Yeah.
Or it instantly recognizes a face in a crowded photo. Or, when it writes a highly structured essay right on demand.
Yeah, it is wild to watch.
It feels like there is a ghost in the machine, you know? Like there is some kind of sentient intelligence just reading our minds.
Right. But the truth is actually quite different.
Exactly. Because when you strip away the sleek interface and actually look at what is happening under the hood, the machine is really only doing one thing. It is guessing.
Yep, just guessing.
And the only reason it seems so magical, the only reason its guesses are so incredibly accurate is just because it has practiced making those guesses billions upon billions of times.
We have this huge tendency as humans to anthropomorphize our technology. We want to believe the machine understands the world the exact same way we do.
Which makes sense because the outputs look so human.
Sure, but the reality is far more mechanical, and honestly, I think it is far more fascinating. What we call artificial intelligence is fundamentally just an exercise in brute force mathematics and, well, advanced probability.
Welcome to the Deep Dive. I am your host, and as always, I am here to be the enthusiastic skeptic. I am the one asking the questions you're probably yelling at your dashboard right now.
And hello, everyone. I'm thrilled to be here.
And joining me to navigate this complex landscape is our resident guide. She has this amazing, unique talent for taking the densest technical literature and turning it into a really compelling narrative.
Thank you. Today, we are going to do exactly what we just promised. We are going to pull back the curtain on that magic and examine the actual machinery making those highly educated guesses.
Okay, let's unpack this. Our mission today is highly specific.
Yes.
We have gathered a huge stack of sources for you. We've got foundational computer science textbooks, university research papers, all the way to practical career guides for tech professionals.
A really great mix of theory and practice.
And we are going to use all of this to decode the core structural concept that makes modern AI possible. We are talking about the neural network.
Because without the neural network, the entire landscape of modern artificial intelligence simply wouldn't exist. It is the absolute bedrock of the current technological revolution.
But before we get into the heavy math of how this machine actually guesses, I really need to understand the branding here.
The branding.
Yeah, I use these tools every day, and I've always wondered why engineers chose such a biological term for a piece of software.
Ah, I see what you mean.
Because calling it a neural network sounds like a very deliberate marketing spin,
Yeah.
Like trying to make a calculator sound like a biological brain.
Well, it wasn't marketing at all, actually. It was a literal attempt to mimic biology.
Wait, really?
Yeah, we have to go all the way back to 1943 for this.
1943. We were building AI back then.
Not exactly building it, but theorizing it. A neurophysiologist named Warren McCulloch and a mathematician named Walter Pitts proposed what we now call the MP model. They were studying the human central nervous system, and they realized that the way biological neurons operate could be described using very straightforward propositional logic.
So they were looking at literal brain cells and seeing mathematical equations.
Essentially, yes. Think about a biological brain. A single neuron receives chemical signals from other neurons through these branch-like structures called dendrites.
Right, I remember that from high school biology.
Exactly. So the neuron processes those incoming signals, and if the combined strength of all those signals reaches a certain tipping point, a threshold, the neuron fires.
It sends the signal down the line.
Yep, it sends an electrical impulse down its axon to pass the message along to the next cell.
Wait, so an artificial neuron in a piece of modern code is doing that exact same thing?
It replicates those 3 exact steps, just mathematically.
How does that work?
First, the artificial neuron receives incoming data, and it applies a weight to each piece of data. Yes. The weight basically determines how important that specific signal is. Second, it calculates the sum of all those weighted inputs.
Okay, so it just adds them all up.
Right. And third, it passes that total sum through something called an activation function. This decides if it should fire the signal forward to the next layer of the network.
Okay, for everyone listening right now who isn't a mathematician, let's bring this down to earth.
Please do.
Let's imagine an artificial neuron is a mid-level manager at a massive multinational corporation.
I like where this is going.
So every single day, this manager receives urgent advice from different departments. All right, marketing is screaming, hey, we need to spend money on this ad campaign.
Finance is probably yelling the opposite.
Exactly. Finance is yelling, we need to freeze all budgets immediately. And then the CEO sends an email saying, we need to aggressively grow our market share.
That sounds like a rather stressful position to be in.
Very stressful.
Yeah.
But our manager doesn't just blindly listen to everyone equally, right? They apply a weight to each opinion based on past experience and corporate hierarchy.
Because the CEO's opinion matters more than a random intern's.
Exactly. The CEO's email might get a weight of 0.8 out of 1. Finance gets a 0.5. Marketing maybe gets a 0.2.
Makes perfect sense.
The manager takes all those opinions, multiplies them by their respective weights, and adds them up. That final number is then compared against their own internal threshold.
Which is the activation function.
Right. If the final number crosses that threshold, the manager signs the approval form and takes action. If it doesn't, the proposal just goes in the trash.
That is actually a highly accurate way to visualize it. And if we want to push that corporate analogy slightly further,
Let's do it.
those activation functions come in different flavors. One common one is called ReLU, which stands for a rectified linear unit.
Okay, what kind of manager is ReLU?
A ReLU manager is very binary. If the weighted sum of opinions is negative, meaning it looks like a terrible idea, the manager outputs an absolute 0. They do nothing.
But what if it's positive?
If it's positive, they pass the exact numerical value of their enthusiasm forward.
Got it. What's another flavor?
Another type is a sigmoid function. This one basically compresses any input into a neat percentage between 0 and 1.
Oh, I see. So instead of just a flat yes or no, it's more nuanced.
Exactly. The manager passes forward a message saying, I am 84% confident we should proceed.
Okay, that makes perfect sense for a single manager. But here is where I get lost with the sources.
Where's that?
Well, if one artificial neuron is just an office worker weighing opinions and passing the buck, how does the entire company, the whole network, actually learn anything?
That is the big question.
Because companies make terrible decisions all the time.
Yeah.
How does this system know if its final guess was actually right or wrong?
This brings us to a concept called end-to-end learning. And it involves a notoriously tricky hurdle known as the credit assignment problem, or CAP.
The credit assignment problem. Okay, so applying our corporate analogy.
Go ahead.
The company launches a terrible product, it totally bombs, the company loses millions. And now the CEO is trying to figure out which specific department's bad advice actually caused the disaster.
Yes, and everyone is pointing fingers.
Exactly.
Imagine a deep learning model playing a game of Go against a human grandmaster. The AI makes thousands of complex calculations, places its stones, and at the very end of the game, there is only a binary result.
It either won or it lost.
Right. So if it loses, how do you mathematically determine which individual artificial neuron, perhaps buried 30 layers deep in the network, made the slightly inaccurate guess that led to the defeat 50 moves later?
Wow. Yeah, the contribution of every single component is incredibly blurred.
Exactly.
Because the neuron that made the final call was just acting on the advice of the neurons before it. And they were acting on the advice of the neurons before them.
It's a massive chain of blame.
So how does it actually correct itself? Does it just start randomly firing neurons and trying again?
Oh no. Random guessing would take until the end of the universe.
Fair point.
Instead, we use something called a loss function, and we combine that with an algorithm called backpropagation.
Backpropagation. That sounds intense.
It's actually brilliant. When the network makes a guess, say, it looks at a photo and guesses dog, and the ground truth is actually cat, the loss function calculates the exact mathematical distance between the network's guess and reality.
Okay. And this distance is the error.
Yes, that distance is the error.
So we have a quantifiable measurement of exactly how badly the network messed up.
Exactly. And then comes backpropagation. The network takes that error measurement at the very end of the output, and it literally walks backward through the entire system.
Wait, it goes in reverse.
Yes. It calculates the gradient, which is the slope of the error, for the final layer. It's essentially figuring out how much each weight in that layer contributed to the mistake.
Oh, wow.
Then it steps back to the previous layer and does it again, all the way back to the input.
That is wild.
It meticulously tweaks the weights, the importance given to different inputs across millions of connections. It does this to ensure that the next time it sees that specific image, the final error will be mathematically smaller.
So it's not just making a wild guess. It has an automated, highly rigorous post-mortem process where it works backward to adjust everyone's priorities.
It repeats this forward guessing and backward adjusting cycle thousands or millions of times until the overall loss function is completely minimized.
Okay, here's where it gets really interesting for me. You just mentioned layers,
I did.
because we always hear the term deep learning. If a standard neural network is just a bunch of artificial neurons doing this weighted math, what makes it deep?
That's a great question.
Does deep just mean we copy and pasted the same layer of neurons 1,000 times to give it more processing juice?
Not exactly. Depth doesn't just mean more raw computing power. It refers to the literal number of hidden layers stacked between the input data and the final output.
Okay.
The key concept here is hierarchical feature extraction.
Hierarchical feature extraction. That is a huge mouthful.
No, it sounds intimidating. This is especially prominent in convolutional neural networks, or CNNs, which are used heavily for computer vision.
Right, for looking at images. So what does hierarchical feature extraction actually mean?
It just means breaking a complex problem down into a hierarchy of simpler concepts. A deep network doesn't try to look at an entire image and immediately understand what it is.
Doesn't just see the whole picture.
No. It uses the depth of its layers to transform raw data into increasingly abstract representations.
Let me try to translate this for you, the listener, because the sources had a really good way of explaining this.
Go for it.
Let's say we want our AI to recognize a picture of a cat.
Hmm.
If we use a shadow network, it's like forcing an employee to stare at a spreadsheet containing 3 million individual color pixels and demanding they instantly say if it's a cat or not.
Which is impossible for anyone to do.
Right. But when we add depth, the entire workflow changes. Layer 1 only looks at raw pixels. It just looks for stark contrasts in color to identify simple edges. That's all it knows. Then Layer 2 takes those edges and connects them into simple shapes. Layer 3 looks at those shapes and recognizes a complex texture, like fur, or a specific geometry, like a pointed ear.
It builds up the abstraction.
Exactly. Layer 4 combines those and says, hey, that's an eye. So by the time we reach the final layer, it has synthesized all these abstract concepts to confidently say this is a cat.
That is a perfect visualization of a CNN.
It actually reminds me of how a career progresses, you know?
How so?
Well, when you first join a company right out of college, you are layer 1. You only see the raw pixels, the daily spreadsheets, the minor tasks. You don't see the big picture.
Very true.
3 years later, as a mid-level manager, you start seeing the shapes, the departmental processes. But it's only when you become the CEO, looking down from the top layer, that you synthesize all of it and finally see the entire business model.
That is a brilliant analogy. Depth is just the stacking of abstract understanding.
Right.
And mathematically, computer scientists proved that deep architectures are exponentially more efficient at representing complex, highly nonlinear functions than shallow, wide networks.
Because they can build on previous layers.
Yes. Depth allows the system to reuse features it learned in early layers to build much more complex ideas later on.
But this leads me to a massive contradiction I noticed in the sources.
Oh!
Contradiction.
Yeah, I was reading through that 2019 textbook on neural networks and deep learning that you sent over. It clearly states that Jan LeCun was using this exact backpropagation algorithm to train a CNN to recognize handwritten zip codes back in 1989.
He was, yes.
1989. That means the math and the architecture for deep learning have existed for decades.
Yeah.
So why did it feel like AI just suddenly exploded out of nowhere 10 years ago? What happened in the dark ages between 1989 and 2012?
Well, the field experienced something often referred to as an AI winter.
An AI winter.
The math was theoretically sound, but it hit a literal physical wall. First, there was a mathematical roadblock called the vanishing gradient problem. What is a vanishing gradient?
Remember how we discussed backpropagation walking backward to fix errors?
Yeah, it calculates the slope and walks back.
Well, that gradient is the signal telling the network how to adjust. But in the 1990s, when researchers tried to build deeper networks, that error signal would get multiplied by tiny numbers over and over as it moved backward.
Oh, I see.
By the time the signal reached the earliest layers, it was so weak it effectively vanished. The early layers couldn't learn anything.
That's frustrating.
And beyond that, the computational reality was just grim. In 1989, it took 3 solid days of compute time just to train a network to recognize a simple black and white zip code.
Wow. 3 days for a few digits.
Yeah.
So their software ambitions were completely bottlenecked by their hardware reality.
Precisely. The turning point, the big bang of modern AI, occurred in 2012 at a global computer vision competition called ImageNet.
Right, the ImageNet competition.
A deep neural network called AlexNet completely shattered all previous records for image recognition. Within a few years, newer models like Senet were achieving error rates below 5%.
Which actually surpasses human visual accuracy, right?
Yes, it is better than a human at recognizing images.
So what changed in 2012 to make that possible? How did we thaw out of the AI winter?
It was a perfect storm of three factors. First, the internet had finally generated massive labeled data sets. For the first time, we had millions of categorized images to train on.
Okay, so we had the data. What else?
Second, there was an unprecedented leap in overall computing power. And third, researchers realized they could use GPUs, graphics processing units.
Wait, GPUs? I thought those were just hardware cards designed to render high-resolution graphics for teenagers playing video games.
They are.
Why does a neural network care about gaming hardware?
It all comes down to architecture. A standard CPU, which is the brain of your computer, is like a small group of incredibly brilliant professors. They can solve very complex logic problems, but they do it sequentially one at a time. A GPU, on the other hand, is like thousands of elementary school students.
That is quite the contrast.
They aren't geniuses, but they can do basic addition, and they can do it all at the exact same time. Rendering a video game requires calculating the color of millions of pixels simultaneously.
Oh, I see where this is going.
Training a neural network requires doing millions of basic weight adjustments simultaneously. The gaming industry inadvertently built the exact parallel processing engine that deep learning desperately needed.
That is wild. So to summarize this, engineers have had the driver's license, the algorithm, since the 1980s, but they were stuck walking.
Pretty much.
Then in 2012, someone finally handed them the keys to a Porsche, fueled by the endless gas of big data, and the entire field just launched into hyperdrive.
That is a great summary. But what's fascinating here is that while the Porsche is incredibly fast, driving it is astronomically expensive. And that brings us to the stark limitations and the darker side of deep learning.
Right, because nothing is a silver bullet. If we have the data in the GPUs, what's the catch?
The catch is that deep learning is aggressively data-hungry and compute-heavy. Training modern models costs tens of millions of dollars in electricity and hardware.
Just to run the training.
Just to train the model, yes. But the far more alarming issue is known as the black box problem.
The black box. Wait, but we just spent the last 10 minutes explaining exactly how the math works. We wrote the code. How can it be a black box?
We know how the system updates its weights, sure. But once a network has billions of parameters, the internal logic becomes completely opaque to us.
What do you mean opaque?
Let's look at medical applications. According to research from Georgetown University's Medical Center, convolutional neural networks are incredibly adept at detecting anomalies like lung tumors or breast cancer in medical scans.
Because they can spot patterns human eyes miss.
Exactly. But as the precision goes up, so do the false positives, flagging totally healthy tissue as cancerous.
And if an AI tells a surgeon, hey, this patient has a tumor, the very first thing the surgeon is going to ask is why? Show me your clinical reasoning.
Exactly. And the neural network cannot explain its reasoning.
Wait, it can't tell you how it got the answer.
No, it cannot point to a specific biological marker and explain causality because it relies on millions of microscopic, abstract data relationships. It essentially outputs a diagnosis and says, trust me.
Trust me. Wow. In high-stakes environments like medicine or criminal justice, a machine that cannot explain its logic is a massive liability.
Completely.
I mean, if a bank uses an algorithm to deny my mortgage, legally they have to be able to tell me exactly why I was rejected. Trust me doesn't hold up in court.
It certainly doesn't. Furthermore, these models are incredibly prone to overfitting.
Overfitting, what's that?
Overfitting is when a network basically memorizes the exact data it was trained on, like a student memorizing the answers to a practice test, but completely fails when presented with a new, unseen scenario in the real world.
Oh, so it looks smart in the lab, but fails in the wild.
Exactly. And because these models are trained on historical data, they mathematically inherit and amplify any statistical biases present in that data.
So they inherit our flaws.
Right. They treat past human prejudices as objective mathematical rules to follow in the future.
This sounds like a massive structural vulnerability.
It is a huge challenge for the field right now.
It makes it really clear that we don't just need software engineers to write code. We need interpreters. We need professionals who can dive into the black box and audit these systems.
Absolutely.
And this actually ties perfectly into the career guides in our source stack. For you listening right now, if you are feeling overwhelmed by all this, but you actually want to pivot your career into the AI space, where should you focus your energy?
Well, the most common mistake beginners make is becoming overly obsessed with mastering specific programming frameworks right out of the gate.
Like which ones?
Tools like PyTorch, TensorFlow, or Paddle.
I hear those names all the time.
Yes, those are the industry standards for building deep networks today. But tools evolve and frameworks eventually become obsolete.
So you shouldn't just be memorizing which buttons to push on the dashboard.
Exactly. True expertise comes from understanding the underlying mechanics we discussed today.
The fundamentals.
Right. You need to understand how the data flows, why a gradient vanishes, how weights are updated through backpropagation, and what specific goal the loss function is actually trying to optimize.
Because if you understand the math and the architecture, you can adapt to whatever new software tool the industry invents tomorrow.
The syntax always changes, but the fundamental logic remains.
So what does this all mean for you? If you take one thing away from our deep dive today, don't be intimidated by the buzzwords.
Definitely not.
What we are dealing with isn't artificial intelligence, it is artificial statistics.
Mm.
The neural network itself isn't inherently smart. It is essentially an empty mathematical vessel.
Exactly.
It is the immense scale of the data and the raw power of the hardware that make it look like magic.
And, if we connect everything we've talked about to the bigger picture, it actually raises a really profound question about the limits of this architecture.
Oh, what kind of limits?
Well, the standard deep neural networks we discussed today, like the ones used for image recognition, they only look at the exact input they are given in the present moment.
Right, like a single static photograph.
Exactly. They have no concept of time.
Okay.
But think about what AI is doing today. It is translating long paragraphs of text. It is predicting stock market charts. It is generating fluid audio.
Right.
All of those tasks require an understanding of sequence. You have to know what happened a second ago to predict what will happen next.
That makes total sense.
So the question is, how does a mathematical model that only understands the present moment learn to develop a memory?
Wow. That is a brilliant point. I mean, teaching a calculator to recognize a cat is one thing, but teaching it to develop a sense of time, to know what information to hold on to and what to forget as a sentence unfolds.
It's a completely different challenge.
That sounds exponentially harder. And that is exactly what we are going to explore in our next deep dive.
I can't wait.
We will be unpacking LSTM's long short-term memory models and dissecting how AI learned the delicate art of selective memory.
It's going to be a great discussion.
Thank you so much for joining us today. If this deep dive finally helped you make sense of neural networks and stripped away a bit of the magic to reveal the incredible math underneath, please subscribe to the show.
And share it with a friend.
Yes, share this with a friend who loves learning how things actually work. We will see you next time.